Hey Brian,
How's it going?
good. How are you?
Good. I did just upload the slides, so it wasn't with a lot of time to spare, but well, like 20 minutes ago. But hopefully it goes well.
Good.
So, are you using reinforcement learning for anything? I know you mentioned it before in one of our earlier emails.
Yeah, I'm not using anywhere right now,
Gotcha.
but that's something always there to like how to play with the reinforcement learning, and I see a lot of articles on this, like OpenAI Gym and things, but never
Yeah.
got a chance to play with it. Yeah.
We're using it in
Gotcha.
the AA program.
Mary.
Yeah. So we're using it in the AA program, by the way.
Oh, nice. Um, that's cool. Yogesh, do you mind enabling screen sharing?
Oh, let me. Yes. Sorry.
Cool. No worries. I feel like that happens on is just part of the regular routine with Zoom. It seems that every call I'm on, there's always requests to the host to screen share.
There are now so many options on that Zoom's panel, like it's hard to keep up.
Yeah, definitely.
I think we can wait for like a few minutes and then
Sounds good.
2, 3 minutes, I guess.
So I do have a call at 4, so I'll have to be uh, having a hard stop then. But
Yes.
just more as a heads up. I mean, it's not. I don't imagine it'll be a problem, but just figured I'd mention it.
I think we just, yeah.
In the past, sometimes I've gone over, but won't be able to today. Shucks.
Happy Canada Day.
Is Canada, or it's Canada Day?
Yes.
Wow.
So there was, Stephen, right? He is from Canada. Stephen Rees. So,
Ah, that's right.
yeah. I think we can get started. I don't.
Sounds good.
Yeah.
All right.
Given that we are just how many? 1, 2, 3, 4, and 2 brands. So yeah.
All right. Well, maybe people filter in as we get after we get started. Anyway, so today I'm going to be talking about reinforcement learning as well as a couple other related topics. Now, reinforcement learning is a pretty big topic. There's a lot of stuff going on there. So it's so my goal for this I don't know, for the next hour or so anyway, is to try to present a brief overview and some related topics so you can get some kind of hopefully enough insight to where if there's a specific aspect you want to get into, you can dig into it more easily. So talking about terminology, talking about some of the basic techniques, but of course there's way too much to cover in simply like a 1 hour period. So just keep that little disclaimer in mind, I guess. All right, so the very basics, I guess, is that reinforcement learning starts with this kind of, I guess, problem, or this kind of setup or problem statement or formalization anyway, where you have some agent that interacts with an environment. The environment provides the agent with a state and reward from the previous, or from the previous interaction anyway, and then the agent can take actions in this environment. So there are a lot of different things that you could imagine fitting into this, I guess, reinforcement learning like framework or problem statement, I guess. So like, you've probably heard of some of the common ones, I guess. There's like, AlphaGo, where the environment would be this game of Go and the agent would be making the moves in the environment to try to maximize its reward, or in other words, whether or not it wins or loses. And then you'd have other, actually maybe it's AlphaGo 0, I think, that was using RL. Anyway, and then you could also imagine things like robots interacting in an environment. There are some things like RoboCup, where where they have robots that are playing robot soccer against each other, and a lot of these have like RL components at some level. Now it's oftentimes, I think in practice like this, it can be a blend of some like scripted things as well as like completely learned behaviors, but anyway. So before we go any further, I want to cover, I had this big kind of wall of text here talking about relevant terminology that'll come up later. So the state, like I referred to here, is something like numerical representation of the current state of the environment. If you're looking at something like, so it really depends. There's so many different ways to represent like the state of games and such. But so for example, in the context of games, they might be using pixels. So then you would have some tensor, some like 3-dimensional tensor really, where you have red, green, and blue values or RGB values for each pixel, and then of course pixels in every row and every column. So that could be one representation of the game state. Similarly, if you have access to the symbolic state, of course, you could represent the same thing in terms of number of entities and entity locations and things like that on the screen. An episode is a sequence of interactions, also sometimes called like a trajectory, until like termination. So like in a game scenario, this would be till the game wins or loses, or till the player like wins or loses. But of course, episodes, how you define this depends a bit on the environment as well. Now a reward is a scalar, it's returned after each interaction. And it's basically what the agent is trying to maximize. The return is usually what they use to refer to is a term that's used to refer to the cumulative reward. So in other words, maybe you play tic-tac-toe and you make, I don't know, 9 moves or something. The return would be the reward, like the reward received at each time step. So the sum of all the rewards at each time step during one game or one episode. An agent is the entity that's trying to maximize the return. So it's the thing that the AI controls. The policy defines the behavior for an agent. Yeah, we'll get into that more a bit later, like exactly what that means. Like I guess I can explain a little now. So it could be like a neural network with a bunch of weights. Given a state as input, it produces some output, which is the action to take there. In that case, this neural network would define the policy. And a state space and action space, these come up a little bit more when you start getting into, I guess concretely you can see it if you're actually adding an environment like OpenAI Gym, but essentially these just define the total space, as the names would suggest, the total space or the space of all possible states or all possible actions. So for example, there's one we're going to see later, which is called cart pole. Cart pole is basically a game where you have a cart and there's a pole standing on it and you want to keep the pole balanced. So the state space, so the action space here would just be a discrete action space with 2 elements. So you could just choose left or right. Well, you probably want to say 3, left, right, or don't move. And then the state space, also it depends a little bit on how you want to represent this. You could go from pixels, where then it would be quite a large tensor. I don't know that where each individual pixel value is in the range of like 0 to 1 or 0 to 255. You probably normalize it first, so probably 0 to 1. All right, does that make sense for everyone before we go any further?
Yes.
It's not the most exciting slide, but unfortunately, if you don't know terminology, it's hard to go much further. Now, another concept that'll come up a lot in reinforcement learning is a Markov decision process. Basically, a Markov decision process is a lot like a finite state machine, except you have states, or like a Markov chain. If you're familiar with Markov chains. If you're familiar with Markov chains, you can think of a Markov decision process as a Markov chain where you take actions, and then there's a probability based on the action you take. If you're not familiar with those, you can just think of them as we have these basically, they're essentially finite state machines. So we start at say we start at S0 here, we can see that there are 2 actions, A0 and A1. If we take A0, there's a 50% likelihood we come back to state 0. There's a 50% likelihood we go to state 2. So essentially there's a decision-making step where we pick an action for whatever state we're in. And then there's also a transition probability once you take that action. So if I'm in state 2 and I take action 1, there is a 40% likelihood that the next state will be state 2 again, 30% it'll be state 0, and 30% it'll be state 1. So in other words, now Markov decision processes are relevant in the context of reinforcement learning because they're used to model the environment. So basically you can think of the environment as something that, again, you know what state you're in. And then you can take some sort of action, just kind of like looking back at this slide before. And then they usually just include a reward on top of this. So then you could think of this reinforcement learning task as given some environment, which is again represented as the Markov decision process. From a certain state, we take some sort of action, it transitions us to another state, and we get some sort of reward. And then we want to just try to move through this and maximize rewards until we end up in a terminal state. All right. So a couple other important I guess formalizations and that we'll see in reinforcement learning are the concept of Q and value and Q functions. So a Q function is essentially saying that given a state at time t and an action taken at time t, what is going to be our cumulative reward, or what can we expect for a reward there. So, and then a value function is just given a state at time t, it just gives you an expected return. Now, it's worth mentioning that although I didn't add this superscript, these are also often showed with a superscript of pi. So pi is often used to represent your policy. So let's see here. Oh, well, it's fine. So, so in other words, when we look at value functions here, then we would say the superscript pi means basically what would be the expected reward return starting in state S and operating according to this policy. Does that make sense?
Yeah.
Cool. And then the Q function, or action value function, is basically we have, it's also parameterized by the policy that we're using, because it's hard to say anything about, you know, how your overall return. I mean, you can speak to reward, but trying to say what would be the overall return of playing the episode out to the end, of course, depends on future interactions. So these all are going to be parameterized by the policy pi. So you can see here, if you want to see the formalization of this anyway, that basically it's looking at the expectation from a trajectory sampled from pi. So that's what tau references here. So this is basically, if we look at all the different ways the game could play out, if we're following the policy pi. Now, it's worth mentioning that the reason why you could argue that we could have a neural network that gives us a policy, or it doesn't really matter what it is. We could have a deterministic policy, and this expectation is still important because, as I mentioned before, we have these transition probabilities. So doing the same actions doesn't guarantee you the same path through the game or through the environment. Anyways, this stuff is, I don't know, it's important, and I think it's important to have seen and get exposed to and stuff, because this is used in a number of different places anyway. Then, of course, people also talk about the optimal value function and optimal action value function. So, like, if you had the optimal policy, what would be the best that you could do? As opposed to, of course, given the current policy that we have. All right.
So the Q function is basically talking about what the return is going to be based on the action that could be taken. And the value function is for a given state, depending on a particular policy pi, and assuming a series of actions that will come out of that policy, what will be the expected return?
Yeah, basically. I mean, both of them are parameterized by both of them depend on the policy itself.
Yeah.
So both are depend on the policy. The value function is just given that state, and then the action value function, or the Q function, is depending on the state and the action. Now, one important thing from this is you might have heard of Q learning before. So Q learning means that we're basically just trying to learn this Q function, because if we knew this Q function and we knew the possible actions at any given state, this kind of implies a policy for us, because we can just try all the actions, and then then just take the max. Does that make sense?
Yeah.
Cool. So, all right. But there are like a lot of different algorithms, but oftentimes you see people talking about value functions and Q functions. So it's important to at least have been exposed to these. We'll talk, like, I have a big slide of just like related topics, which is just more for us to, if people have more questions in any of these spaces, then we can dig into them a little bit more. So one thing, I have a lot of these links to this OpenAI spinning up document. I have links to it both in the README and in the slides. I would really recommend this. I'm a big fan of this document. It's pretty comprehensive, but also has sections that are a bit more pragmatic as well. And they talk about a lot of different, like, approaches here. I mean, you can see Q learning right here, which is exactly what I was just referencing to. Basically, if we can approximate the Q function, then they can then we can just take the maximum action given the value after we evaluate the Q function for every action in that given state. So they have things like some of the standard, I guess, baselines or ones to start with. If you're trying to use DeepRL, is like DQN, which I think they were learning how to play one of the Atari games from Pixels. Yeah, here we go. Playing Atari with using just Q learning, but using a neural network or a deep neural network to as the to approximate the Q function, or to learn the Q function, really. So they're going directly from Pixels here, so you can imagine this state space is quite large. Anyway, there are other options which are doing things like policy optimization directly. So in other words, which is a lot more like what we saw when we were talking about the neural networks, where we have some sort of loss function that we just back propagate and update directly. But then there are other ones too, which look at like actor critic and all sorts of other approaches as well. Actor critic, where you have a different model that's trying to approximate the value function that's basically separate from the actual policy or actor itself. They kind of feed into each other. Now, so we'll talk about this a little bit more later, but there are a lot of offshoots and things like this, and a pretty, again, reinforcement learning is a pretty big space. There's a lot of different things to dig into, but like some other concepts that are valuable, I think, is this breakdown between model free and model based RL. So when they're talking about the model here, basically they're referring to this environment in some cases, in some cases, gaining these interactions with the environment. So like if you think about like robotics or a lot of times you're interacting with things in the real world rather than in simulation, it can be really expensive to train for a while because it takes a lot of time to actually collect that many interactions. So that's where people started this offshoot of model-based RL. So in other words, can we learn a model of the environment, which is what they often, which happens in kind of this whole big tree here, I guess, anyway, or subtree. So basically, in this case, it's like if we look back to this slide. So we interact with the environment, but we want to actually learn a model of the environment so that we can interact with our model of the environment and then keep updating our model of the environment based on the real interactions. Basically, just another area where people try to be more sample efficient with respect to interactions in the environment itself, so that they can actually spend more time training, if that makes sense. All right. Okay, so I'm going to start transitioning over into one of the hands-on examples, just to give, I don't know, to get a little bit of hands-on experience of what this looks like in practice. But before we get started with it, I wanted to always cover, or at least mention what OpenAI Gym was, because we'll be using it in a moment here. Now, OpenAI Gym has basically become the standard for, or the standard API really for reinforcement learning, or at least specifically the reinforcement learning environments. I mentioned before that we have these state and action spaces. In an OpenAI Gym, basically they define their own state and action spaces, and then and of course like reward functions. So we have to be able to compute a reward to return to the user, and then of course it actually has to interact with the environment itself. But even just this interface of knowing what the valid states are and what the action space is and stuff is enough to let a lot of these algorithms just sample from the action space and then do this sort of exploitation trade-off. But anyway, let's jump into this example. All right, so I'm going to show, so we're going to walk through an example here where we are training or using DQN, or basically training a neural network to approximate the Q function using, or in this environment called CartPole. Oh, one thing that's, I guess, worth mentioning anyway is OpenAI Gym it does have a huge amount of environments. Oh, let's see, and it's pretty easy to extend and things like that. So it's really popular, and And it's nice because there are a number of frameworks that, oh well, I was hoping I'd have a huge list of them somewhere, but anyway, it's fine. And it's nice because there are a number of frameworks that have implementations for these various reinforcement learning algorithms. And of course, if you're conforming to this API or this standard, they tend to just work out of the box. So I'm not saying that it will learn and things like that will work out of the box, but you'll at least be able to train the network out of the box. Sometimes these can be sensitive to a number of different challenges, like I mean, I'll talk about more of them a little bit later, but there are things like sparse reward function or sparse rewards and stuff can be really challenging when you have dense state spaces. So sorry, sparse rewards means that you have a lot of decisions to make before you get any reward. So so for some of these environments, you might. So suppose you were playing a game like chess. You could imagine that your reward function or the reward that the agent sees is just 1 if it wins and -1 if it loses. But that could potentially be a really large number of actions, and there could have just been one move where they made a mistake that caused them to lose. That happens, I don't know, maybe 30 moves ago. So this can make, of course, learning pretty tricky. Anyway, so in this first cell, we basically just have a lot of the standard things. Setting the device, so we're using GPU if it's available, and a bunch of imports, including this creating our environment and saying that we're going to use this again cartpole environment. One thing that came up with DQN was that they use a experience replay memory. So basically, they interact with the environment, they keep a buffer of these things, and then they train the queue, the neural network, on this collected experience. Now this is related to, I mean, there are some benefits, or a number of benefits to this. Some of them actually came up when we were talking about training neural networks in general. If you remember, if you were here for that session, Peter had mentioned how it's important to shuffle your data, because if you don't shuffle your data and you're doing mini batch, or you're training using mini batches, you could get different biases in different segments of your data, which could basically cause you to keep moving almost in like a cycle. Does that make sense?
Yeah.
Cool. So similarly, one thing that the replay memory can kind of help with this, because now instead of because you can imagine that there could be temporal biases when we're playing a game. So it's helpful to collect a buffer of these and then just sample out of it. So you can see here that our replay memory class here is doing just that. We're sampling out, we're saving a bunch of transitions. So in other words, the current state, the action, and the next state, and probably reward as well. Here we go. Yep. State, action, next state, and reward. And then we sample out of this. Okay. Now, okay, I mean, I guess I have time. I don't really need to rush. I was just gonna say, like, there's so much background, so many things that can be talked about here. So for example, one thing I kind of glossed over a little bit is this idea of when we're training these queue networks, or training something to like approximate the queue function, we won't know what the total return is until we've completed the whole episode. However, that kind of sucks because that means that we can't train very often. So we have to actually play a whole game before we can do any training at all, rather than trying to improve while we play the game. Because also, we mentioned before that these queue functions and these value functions are defined for the policy themselves. So in other words, these are on policy approaches. So it's important that when you're using these, like if I was training my own model and Yogesh was training his own model, we couldn't share data because my data will only reflect would reflect the return that I would get if I gave my data Yogesh, he would have examples of a state action pair and the return if he followed my policy, not if he followed his own policy. So so this can be kind of problematic, because then it's hard to like learn to approximate the Q function when the data is not, in fact, how the Q function would behave using your policy, if that makes sense. So, so anyway, one of the, let's see. Oh, so one of the problems anyway, this is relevant too when we're thinking about when we train, because if we train through a whole episode, it's not like we can like, and I guess we can try to approximate that one, but it's tricky because our Q function is, our approximation of the Q function is central to our policy. So changing that too much means we're no longer using data from our policy, if that makes sense. Because we start to diverge basically because our policy changes from what we were using when we collected the data. So anyway, my point is that it's valuable to be able to train more frequently in like smaller steps and stuff, so you don't have to just train at the end of every episode. The one way that we can get around knowing the entire return is to actually would use what they call temporal difference learning. Now, I think we should be seeing that here. Yeah, here we go. So basically, temporal difference learning means that here we go. So so basically what we do is we look at like our essentially consistency of our Q function. So anecdotally, you could imagine that if I wanted to see how good, like if I'm driving somewhere and using Google Maps and it says that it's going to take me 30 minutes to get to my destination, and like 20 minutes later, I'm not anywhere close to halfway there, and it says it's still going to take 30 minutes. I don't need to have completed my trip to know that that's inaccurate. Because what we can do is we could look at basically how accurate its first prediction was. So we could say that a few steps later now, assuming that it's right now, or at the end, the second time I look at my GPS and it says that there's 20 minutes left, assuming that's correct, it should have been 10 minutes from the first prediction, because it said that at the beginning, it said it would take me 30 minutes to get to my destination. 20 minutes later, it said it would take me 20 minutes to get to my destination. So we can actually start computing a loss there, because we can see that there's an error when looking at that step. So that's, in other words, we look at the difference between these two time steps, hence temporal difference. So it's temporal difference learning. All right. So basically, we start to see this when we start looking at these Q functions. So they essentially try to break down our actually, we can see it right here. So this is the temporal difference error. Basically, we have the error is equal to the Q value, or the predicted return, minus the reward at that state, so R, plus this. Now, I haven't mentioned this too much, but a lot of times they have these decay rates. Basically, you want to prioritize early rewards rather than having them run on forever. So, and I should have probably mentioned that with the cumulative reward. Oftentimes they include this, so they would rather have early successes rather than running on forever. So the whole return in this context, they're using some sort of they're using a decay factor, or discount factor really, gamma, and then and as they mentioned, it also helps to ensure that it'll converge, because you could imagine that there might be an environment where you just keep collecting reward and it doesn't seem to end. So even if the environment goes on forever, the fact that we have this decay rate means that we can ensure that it's going to converge. Anyway, so if you remember back to like your geometric series, you can, I guess, have the proof there. But anyway, so in this case, what we're doing is doing this temporal difference. We're computing this temporal difference error, and then we're going to just train it using we're going to train our model, which is predicting this, which is approximating this Q function using this error. So we take the state at the beginning minus the reward that we got from that time step, and then use that gamma factor, and then try to approximate what we would do next. So get the best, or the largest, predicted return given all the actions. In other words, this comes out to the action that we would take at that step. So, or the return produced after taking the action at that step that we would take using this Q network, or this by following our Q function. Anyway, so
Uh,
other questions there? Questions would be great
yeah.
because I feel like I don't know if it was the most clear.
Here in the reinforcement learning, we can look at the environment. We can do the Q learning, and the problem is that the network that we learned earlier is no longer applicable because the environment has changed, and so we have to relearn. We can use, instead of relearning from scratch, we can use something called temporal difference learning, so that we can do the relearning a little bit faster than what we would have. What
Yeah.
is not clear is that how does it make it faster?
So basically, we can train without having to wait to finish our episode. So that's what I was trying to say before. So in other words,
Yeah, I mean, I understand, like you gave the example of Google Maps. While you are in the middle, you already know. So what essentially you are saying is that you are constantly doing this temporal difference learning.
yeah. So yeah, because in the Google Maps example, we would notice that our GPS estimate is overly optimistic. So we would know that we should probably add more time to whatever it said. Similarly, so and that's kind of like, okay, again, this I'm trying to capture the intuition here, but basically basically in this this kind of simple example, if we knew that it was overly optimistic, then we knew that we would know that if we could improve it, we would probably make it a little bit more pessimistic and add time to our estimate. Similarly, in this case, it captures some of the same intuition in the sense that it looks at the earlier prediction and then expects it to follow this. They call it the Bellman equation. So basically, the same type of thing that we referred to in the GPS example, where we expect that my cumulative return from my current state should be equal to the reward I get in this next time step plus my return at that step. Does that make sense?
Yeah, but so we can use this method to guide learning in a specific way to maximize our reward. But still, what is not really clear is that if you think about the learning process itself, that computation that goes on in learning will still be the same, right? I mean, it's just that we are guiding it in a right manner based on this temporal
Oh,
differences.
yeah. So I mean, it will make it more fine grained. So I think what I was trying to say before and didn't do a very good job of it is that it's not like we could play one out to the end and then just train on that. I mean, we could just train on it a ton, I guess, but as we keep training on it more, the one thing that's a little bit odd is that our policy does start changing, which means that the tricky thing with Q learning is that improving your Q function changes your policy if you're just using the Q function to determine what you do. So it's not like I could just collect one sample and then just try to train on it a huge amount for multiple reasons. One is that it would basically this data would end up being off policy once we train more. So let me put it this way. You could imagine that since it takes so long, we just split this into 2 steps. We just to run a bunch of episodes out with a kind of a really dumb predictor, and then we just train on all this data until we get something that seems like it works. But the tricky thing there is that okay, anyway, the tricky thing there is that it's again there's this tension between like improving your Q function and deviating from the policy that created the trajectory of the data. Anyway, it's not I don't know if it's I don't think it's probably the best example of the improvement of temporal difference learning. I would actually say it's probably not. The better example is probably just being able to train without having to wait until you've completed a whole episode.
Mm-hmm.
But I mention it. Yeah, the reason why I was initially mentioning it was just more because since these functions are dependent on the policy that you're using, it'd be tempting to try to take an approach like you do in in a lot of other supervised learning settings, where you just collect a huge data set and then you just train on it. So you could imagine trying to do something like that to learn this Q function. But the problem would be, even if you were trying to, collect a whole bunch of episodes and then just keep each episode together and train on the whole episode, would be that your data would not be on policy anymore, or your data would not really give you the return following your current function. Does that make sense?
Yeah.
So it's more of a counter, I think, to one way that you might try to get around this only being if you were just only training at the end of episodes. In other words, like collecting the whole episode. So
Right.
I didn't do the best job of saying it the first time, but hopefully it makes a little more sense now.
So one important thing is that in the real application of this, when the environment is actually constantly changing, is that if you could do the Q learning, relearning in some sort of anytime fashion, so that you have a limited time budget in which you have to relearn and apply the new policy on the system. So in any time algorithm for relearning will be really nice. I'm not sure though how we can do that.
Wait, can you say that one more time? You're saying an anytime algorithm for relearning?
Right, because we have like limited time budget. If we are in a real world and things are changing or something new come up that the original policy doesn't really already apply, but you have limited time in which you can relearn if you have a capacity to learn in that time frame and then apply an updated policy. So you have a limited time budget, and if you have an anytime algorithm that gives you a better and better learned algorithm or better and better learned policy, depending on how much time budget you provide it to. So that will be a really nice algorithm, right?
Yeah. So I mean, in a way, since this iteratively improves on the previous one, you could argue. I mean, a lot of times when you're training these, so it's tricky because a lot of times when you're training these reinforcement learning algorithms, of course, they're collecting data they're usually collecting this data based on the policy that they're almost, I'm trying to think of any exceptions, but they're almost always collecting samples and interacting with the environment based off of their current best policy, especially in the on policy case, because you have to. Because it's important in the on policy case that the data that you're collecting was generated from the policy that you're training or trying to improve. Right. So in that sense, they often are kind of like anytime algorithms. The tricky part is that like in practice, when you start getting the guarantees and things like that, things can start to get a little tricky. Right. Just because because there can, so for example, if you because one thing that's different in reinforcement learning and imitation learning, or really just this MDP setting, than in like supervised settings or these the other examples of machine learning that we brought up before, is that the policy itself like determines the data you see. So in other words, like if you start off and you have a policy that's really bad and just loses right away, the only examples it's going to see are losing like right away. Now you're hoping, and we'll see this actually coming up here. You hope usually that that eventually it stumbles across something that helps it do better. and this is usually what they refer to as the exploration and exploitation trade-off, because sometimes these models, since there's so much uncertainty and they don't really know, like it's not like they are necessarily, because when the data and these interactions are again generated from the policy itself, it's not like they're getting a unnecessarily unbiased and objective entire data set of the environment. You know, they're getting the data that they've interacted with. So a lot of times they introduce exploration, where they just try to get it to get out of its comfort zone, so to speak. Because sometimes you can get these scenarios where the environment learns something that's really suboptimal, but it learns it because it seems like it's basically like getting stuck in a local optima, or local minima, depending upon, I mean, I guess optima, since we're looking at reward function, or the reward or cumulative return. But so here's an example. There was this there's a game that I've trained AI for, just kind of like, I don't know, playing around and stuff. And it's like a real-time strategy game. So you have like, you know, sword, like archer, people on horseback, and like infantry and stuff. And there's one scenario where the AI was trying to control. I was trying to train an AI to control some of these like cavalry archers, basically, and teach them how to defeat spearmen who had like an attack bonus. So in a head-to-head fight, they would lose, but they could hopefully run around them and avoid them and still attacking them and win eventually. Now, in this case, I had actually played with the reward function to penalize the cavalry. So actually, even without that, when they start off, a lot of times what you end up learning at the beginning is to just run away, because they find out that when they try attacking at all, although there is a way to attack and run, oftentimes if they attack too much, or they're a little bit too biased towards that, then they just get attacked until they do, and killed and get negative reward. But they can learn that running away is good, and then just run away the whole time and almost never attack. So so my point is that one of the complexities that comes in here is that is really from this it's easy to find this local minima, like just retreating and never even trying to win, which seems like a good idea because it's much better than some of the other strategies that have been that they've tried, but they've never seen an example where there was intelligent behavior where it actually did what you were looking for. I'm hoping that makes sense. I'll take people's silences, maybe. Oh, all right. So what's this error is just because because of, I think, how X11 is configured on this cloud instance. But basically, in this example, we're creating a neural network. It's a convolutional neural network, so it's giving access to the pixels, pixel representation of the stage. So in other words, it'll see pictures of, you know, like this. I believe this one is using frame stacking. So in other words, it's representing the stage not as a single image, but as like 2 images or 3 images, so that you can see if it's tipping without having to use a sequential model. Now,
hey Brian.
Yep. Sure.
What is the output of that neural network?
Sure. So the output of this neural network is let's see. So if we we can step through this guy, and we can see that the outputs is one of the constructor arguments. So let's see where it creates it.
So would they be the actions, or?
So here it's so in this case, what it's outputting is a linear layer that has where the dimensionality corresponds to the number of actions. So in other words, this is so I believe this is actually going to be computing the Q value for every action at once. So in other words, here. So So these are the number of actions. This is passed to the deep queue network. The deep queue network has an output, its last layer, so they call the head, has that number of actions. So again, so a tensor that should contain the expected returns given that state, and each action, where each action corresponds to the index in the output tensor or output vector. If that makes sense. Here it explains it here. It returns a tensor where this is the left value. So the left expected value and the right expected value. So this is the expected return if you go left. This is the expected return if you go right. Does that make sense?
So it's just, so is it predicting for like, is it giving a percentage? So if you go to the left, it will be this much of percentage accuracy.
So it's since the Q function returns the expected return. So in other words, the cumulative reward starting at that state, it's actually treating this as a regression problem.
Okay.
So this is, so in other words, given a state, the output of this would tell us if you move left right now, you can expect to get, I don't know, maybe 20 points. You move right, you can expect to get 30 points.
Okay.
So then you would probably pick right. Does that make sense?
Basically, it has two outputs at this point, and it is just giving values to the two actions, like the left
Exactly.
or right.
And those values correspond to what it believes you can expect as a reward, or a cumulative return if you follow that. So if you go left, you can expect to get this much cumulative reward. If you go right, you can get this much cumulative reward in expectation, of course.
Now, is it a trained model over there, or is it just doing the prediction of the regression?
So this model is untrained. So this, of course, is just a constructor for it. Here we're actually loading. So here we're just creating it, and this walkthrough should. I'm wondering why I ran into a little error here that I have to. Oh my goodness, it's trying to show the screen again. Screen. Where? Here we go. Let's not display anything. See if that helps. Okay, let's see what 11. Here we go. I was way off. Oh, dang it. Done. So I should have probably pulled this down and run it on my local computer. I might have to just show it. It would just walk through it and not run it actually here.
Yeah.
Basically, yeah. Okay, so essentially, and I'm running a little short on time, but all right. So essentially what's happening here is that it has a couple helpers here for the environment, just to make sure that it's in the right, that basically doing the pre-processing of the stage. So it's pulling off some of the extra pixels at the top, because as we can see here, there's a lot of white space. So just some of this kind of data cleaning here. And then it should also be stacking them. Let's see, squeeze. I'm expecting it to be stacking, but maybe it's not. So sometimes they use frame stacking, again, just to try to capture motion, because oftentimes motion matters in these games. You know, if something moving toward you or further away, you could imagine if you were playing Pong without frame stacking or any idea of the direction you're going, it'd be really hard to learn. So this is creating a network with the appropriate input size and the output, which is the number of actions, which, as Yogesh was asking about, corresponds to the expected return, taking each of those actions. Here they, and this is something that's in DQN or specific to DQN, they have a policy network and a target network. So basically this tries to keep it from like wiggling too much. So basically it uses the one network for a while, then uses one to update the other, just so it has a kind of a stationary like benchmark or comparison point. Then anyway, and then we have these, this is the actual training loop. So this is going to compute like the, let's see here. All right, so we collect all the interactions, and then we have these batches for the state and the action and rewards. And let's see, here we go. We should see where it actually computes right here. So this is the expected state action values. This actually should look familiar if you break it down looking at the previous ones or previous thing. This is really the basically the Bellman equation again. So this is the next state value times the decay factor plus the reward. So this is how we'd, let's see, yeah. So basically the reward that we have plus the next state value plus gamma should tell you how much you'd be improved, should give us this kind of, what the prediction is expected to have been. So basically I guess kind of test this internal consistency. And then they are computing the loss and then just updating their Q function accordingly. All right. So I'm running short on time, so I'm not going to step through all of this in individual or like line by line. If there are questions, people can always email me, or maybe we can talk about this more in like the next session or things like that. A few other things that are worth checking out is that, so I did make a list of kind of like related concepts and topics. Some of these came up during the course of like our walking through the, like some of the, like the taxonomy that we saw in the spinning up thing, like if it's inexpensive to interact with the environment in terms of time, you can use a model to just learn the transition dynamics, hence model-based reinforcement learning. It's always important when you're actually looking at specific environments to think about if it's deterministic or stochastic. So if it's a completely deterministic environment, I believe they did this in a Mrs. Pac-Man paper out of Microsoft Research in Canada, or maybe Maluba, which was bought by Microsoft Research, or bought by Microsoft, where they beat Mrs. Pac-Man and got the highest possible score. And I believe in that case, once they beat a level, since the game was deterministic, they just memorized the actions for that level. So in that sense, they treated the reinforcement learning policy more like a search. Because once they found a solution, they could just memorize it. All right, then there's another thing that has to be considered, and I talked a little about on policy versus off policy. Some algorithms can work with any data, so you can just collect a bunch of data. So it doesn't have to have been generated by the policy you're trying to improve. Others, like DQN, require the data to be on policy. There's also another big consideration is exploration versus exploitation. I kind of referred to that a little bit when I was talking about this game, where sometimes you can find this thing that seems like a local optima, because and this problem of running into these local optima is even stronger in this case, because the policy that you're learning is really influencing the data that you find. So it could be that it's nowhere. So it could be that you can see how your policy then can really bias your data set. So there are some things like in DQN, they often use this epsilon greedy exploration. In other words, they set some value, like maybe 5%, which means that 5% of the time, their policy will pick a random action. And then the 95% of the time, or the rest of the time anyway, they will they actually evaluate the Q function and take the optimal choice, or what they believe to be the best choice based on their current approximation of the Q function. Other ones like, okay, so one other thing before we get into that. If you have an environment where the actions don't impact subsequent decisions, you could imagine this being like if you're making a website where people come to it and you try to show them where it's kind of just one-step decision making. You want to show them the thing, like you want to basically have essentially clickbait. You want to show them the thing that's most likely for them to click on it. This would be, and maybe you have some information about the user. This would be a scenario where you'd want to use a multi-armed bandit, because it's not really a MDP where you can transition states. There's only one state, so it's like a stateless reinforcement learning setting. In these settings in particular, they have some examples where they have exploration built into the algorithm. And then there are a lot of other discussions about being able to use like imitation learning to warm start the model and things like that. There's all sorts of kind of crazy things. But I have a link of related resources that are worth checking out, including RLlib, which is one that I've used in the past because they have implementations for a lot of these algorithms that we care about. And these algorithms, I could see here. They have a list of algorithms somewhere. Here we go, RLlib algorithms. So, and this is kind of nice to go through. They link to all the papers. They talk about what's supported in terms of actions and such. All right. All right.
Stop now here.
Yeah, sounds good.
We are 1 minute short of 4, so.
Yeah, no worries. I don't mean for it to take so long, but I wanted to at least point out some of those other things that I have linked, because although I didn't get to cover as much as I was hoping to, hopefully those are still useful. Are there any other questions? All right, if not, I'm gonna pop off because I have a meeting in 0 seconds now, I guess. I was gonna say 30 seconds, but looks like it already changed. Well,
thank you very much, Ryan.
I hope some of that was useful or helpful. If there are any questions, again, feel free to shoot me an email, or we can talk about extending it again next week or something.
Great.
See you later.
Have a good one. Bye.
You too. Bye.
Bye, everyone.